I have been working on the last year using stopping cosmic muons to do energy calibration in the CCM detector at Los Alamos. And before I get too far in, I would like to thank the entire CCM collaboration, and specific thanks to Dr. Smith for all of his help on this project, as well as to Darcy Newmark at MIT and Dr. Austin Schneider at both Los Alamos and Texas A&M University. Just a very quick rundown of what the CCM detector is. It is a 10-ton liquid argon cenylator detector that uses 200 8-inch photomultiplier tubes on the inside, which are these guys right here, as well as 28 1-inch photomultiplier tubes on the inside the veto region. And these PMTs will then detect light that is produced from particles that stop in the detector. And then just what the detector eventually will be doing is potentially looking for dark matter using a tungsten cube that's right here that is being impacted by 800 MeV protons produced within the accelerator. And those particles that are produced are most likely going to be pions and other particles, which hopefully are a main source of dark matter. But in order to do all this stuff, we first need to calibrate it, and this is where the first part of my project really came into, was actually looking at particles to do the calibration. And I picked cosmic ray muons that stop inside the detector that produce Michel electrons. But in order to actually detect those particles first, I had to actually trigger on them, which is what these things right up here. These are cosmic wash detectors. So there are 6 pairs of them. Each pair looks like this. As you can see, this one was actually taken at Riddle here. And then these will then trigger, giving me a start time for when to look for these particles. And then once these particles are inside the detector, they can stop producing Michel electron following this blue distribution here, with you have the E plus and the nu mu bar. So this is the anti-muon neutrino. And this equation right up here is what gives you this line. And this is really what we're looking for, is this blue curve to get a distribution, because it has a very sharp cutoff at exactly half of the momentum of the muon, 52.5 MeV. So this right here is what my data looks like. Specifically, it is this strong muon pulse here, and then it decays, and then the light decays, and then you get a Michel electron pulse. And this is really what I'm looking at, because I can figure out exactly what the upper bound on this is, and that'll tell me the exact upper limit of my calibration value. But in order to actually get that, first I had to check to see if I actually had Michel electrons, because it's impossible for me to really tell what my particle is immediately. So what I first did is look at the time spacing, this delta t, between the start of this muon peak and the Michel peak. And then I plotted those on this distribution here with this equation right here, using these ratios representing the ratio between mu plus and mu minus, as well as also having a capture and a decay coefficients, these tau cap and tau naught. And the capture is approximately 600 nanoseconds as like the accepted value, so mine's a little on the low side. But the tau naught is roughly around 2.2, which is accepted as the value of the lifetime for muons that decay into Michels. And now that I was confident that I actually had Michels and what I was seeing, the next step was to subtract out this background baseline that was produced from the Michels. And so using this equation, using a Gaussian to start off with to get this peak, and then 2 exponentials, one for the singlet light, which is the short-lived light, and the triplet, which is this long tail here, subtract out, because if I don't do this, I'm going to have energies that are above 0, which will throw off my calibration. And then once I have subtracted it out, I am left with basically this, which is a nice baseline right around 0, and then just the Michel itself with its own tail. Doing this then, I then integrated over 40 nanoseconds and 90 nanoseconds to just get 2 baselines for how I was going to be doing my integration, which then produced these plots. So this one right here is the 40 nanoseconds, this is the 90 nanoseconds, and unfortunately, as you can see, they don't follow the what we expected nicely. So that was something that we were a little concerned about, and we didn't know what was going on. So the first thing we decided to do, really, was then look at what caused these big spikes right around 0. There were 3 ideas that we really came up with. The first one was corner clipping muons. The second one was just geometric inefficiencies within the detector. And the one that I've been focusing on more recently is events near the edge of the detector. So this right here is just one run, just so you can have a general idea. So the first thing I did was then found the location of all of the particles in here. And then I basically just cut all particles outside of 0.7 meters from the center of the detector as just like a guess to start with. And almost all of them that were cut out were in this low energy bin right here, which I was very happy to see. Unfortunately, there are still quite a few remaining in that low energy bin. So some of the more work that needs to get done is to just continue looking at what caused those, as well as just finding out the sources, figuring out what other ways to reduce the events, as well as getting better lifetime measurements to actually make sure that we are 100% confident of what we are seeing. Thank you. Questions?
What was the motivation for 0.7 meters to a meter cutting out as opposed to maybe 0.6 or 0.5? Do you think you might find a high grouping of them at those low energies as well if you decrease that radius?
So unfortunately, I was not able to add this on this slide. I did have a distribution of the radial distances, and they were pretty consistent up to about 0.6 or so, and then they started falling off pretty rapidly. I have previously done 0.5, and it started cutting out a lot more in like this region right here. So I was like, okay, I'm going to keep it at 0.7. And actually recently I found a paper, actually Dr. Smith found me a paper from the mini moon experiment that they also had similar issues where they had this big peak, and they also cut it right around 0.7. We have a fairly similar size, and I was like, okay, I'm confident in my 0.7 cut.